Hello, good morning. I'm Javier Conde. I'm a assistant professor in Universidad Politécnica de Madrid, and I'm going to give you this presentation with David. David is an expert in AI inside FIWARE, and he is leading the AI group inside FIWARE. And today we are going to teach you this webinar that's about merging LLMs, generative AI, with the FIWARE ecosystems. LLMs are large language models. So the agenda for today is going to be this one. First, I'm going to give you a brief introduction about what's generative AI and LLMs. Then I will explain Retrieval Augmented Generation RAG, that is an architecture that is used by LLMs to make them more powerful. After that, we will explain an implementation of this RAG architecture with the FIWARE ecosystem, because it provides you a lot of advantages and a lot of possibilities that the FIWARE ecosystem offers for LLMs. And the last part will be a demo, and we will show a Naples Turing use case about the ideas of this webinar. This is just a demo and a use case, but I'm sure that you will have new ideas about how applying this architecture with FIWARE. And the last part will be a summary of the most important things that we have been talking in the presentation. So just to begin, I want to give a brief presentation about machine learning, AI, because it's important for you that you know what we are doing and the things that are right now, because AI is a hot topic today, and we need to understand the basic concepts. So I will be very brief. In this slide, you have in the top the traditional programming, in which you have a program that you have coded and data. And with this input data and a program, you obtain some results. Imagine a code that only make ads. You have the program that they make ads, and the data can be two numbers, and the result is the add of both numbers. 1 plus 2 is 3, for example. In machine learning, it works different. We have the data, the input data, and the desired results. In this case, for example, we will have 1 and 3. And the machine learning, what we make is to train a program that in machine learning it's called model, that gives us the program that can compute the results. So we can use this concept and join both things. First, we have the input data, the desired results. We build the program that is called model. This is the training phase. And then we can use this program with new input data to make predictions and obtain a result. So this is very powerful, because with input data, with good results, we can make programs that can predict things. As an example, you can predict the value of a house, for example. With input data can be the size of the house, the location, the floor, whatever you can imagine that it's important for predicting the price of a house. And the desired results would be the prices, the value of that house in a lot of examples. Here the key is that you need a lot of examples to make these programs, to make these models work well. And after that, you can make predictions with new input data of new houses that you don't have used in your training phase. So I have a new house of this size, in this location, in this floor, etc. And with the model that you have trained, you can predict the value of that house. Of course, the model has a performance and does not always answer the right result, but the better the program you have, the better the model you have, the better results you can get. So that's the idea of machine learning, and it's the basis of everything that is happening today. Artificial intelligence and machine learning is very wide. You have a lot of disciplines. Inside machine learning, you can find deep learning. Deep learning are neural networks. Neural networks is an architecture and a structure that is based on the ideas that I have explained, but with a specific architecture that is based on neurons. They work like the neurons that we have in our mind, more or less, in the terms that you have a network of neurons that are connected. And with all the connections, you start from input data and you can get output data. These structures are really, really complex. The idea is really simple, but the structures are huge and really complex. But the true is that you can get very, very good results with deep learning, with these neural networks. Inside deep learning, we can find generative AI. The idea of generative AI is the kind of AI with which you can create new things. When I say create, you can create new images, new videos, new audio, new text, any kind of information. And inside generative AI, there are large language models that are the ones that we are going to treat today, that they are specialized on generating text. And with that generation tasks, you can do a lot of things. So what are the bases of large language models? The idea, it's really simple. And I'm going to be a bit simple because if you go deep, they get complex. But the general idea, it's really simple. The LLMs, what they do is to predict the next word. I'm always going to talk about words, but the truth is that they not predict words, they predict tokens. Now I'm going to explain why, but it's going to be just to clarify and to be a bit right. But after that, I will always talk about predicting words. So in this example, you have when the dog saw the thief, and the model, the large language model like GPT, that maybe it's the one that you are you know the best, will give you the probability of all the words. So the probability of word barked will be very high, but the probability of word pizza will be very low. So you will have the probability of all the words. Here there is a problem. If we are predicting, or the model is giving us the prediction, the probability of all the words, imagine we have in English a lot of words, but we have also a lot of words in Spanish, in Chinese, in any language. And as you know, ChatGPT can answer in multiple languages. So the result would be that this list of words, that they would be all the words that exist in all the languages, will be huge. And it wouldn't be possible to have a model that will predict all the list of all the words in all the languages. It would be a very huge model, and it would be very slow. So the idea is that they will give you tokens. Tokens are just pieces of numbers, and with these tokens that are 30,000 tokens more or less, it depends on the model, you can build all the words of all the languages. So it's a balance between having not so many words, not so many tokens, but you need a lot of tokens to being able to create all the words in all the languages. So the idea is that they are going to work with tokens, but for us, and in the rest of the presentation, I'm going to say words always, because it's going to be easier to understand. So that's the simple idea of this revolution, is models that can predict the next word. Like the old models of your mobile phone that predict the next word that they didn't work really well. In this case, they are working really well because the technology has evolved. We have an architecture that it's called transformers, that it's very powerful, and we have big data and the possibility to train these models. The training phase that I have explained here, we can train with all the information that we have in internet. So these models have been trained with all the information of internet to being able to predict the next word. Okay, so now we have the possibility to predict the next word, but we can make this in a loop. So we can create long text. We start when the dog saw the thief barked, then we can introduce this sentence to the model just to predict the next word. When the dog saw the thief barked too, to scare, etc., etc. So we can take the simple idea of predicting the word to predict long texts. So this is the basis of LLMs, the basis of ChatGPT, Gemini, and all the models that you know. Here, the important thing is how you select the next word. You have different possibilities. These different possibilities give you this kind of graphs, of this kind of trees, in which you have the possibility paths that you can take. So one possibility is to take the most probable path always. In this case, the nice woman. So I will always, if I always take the same path, I will always take have the same result, the nice woman. But this is not how humans work. We are animals that we are very diverse when we talk. So the people that design these models, they have different strategies for selecting this path. One strategy is throw a dice with the probability that the model gives you. So half of the times you will take this path, the nice, but the 40% of the times you will take the path, the dog, and the rest, the car, and you are throwing the dice every time. That's why these models always answer you different things, because they are designed to not returning always the most probable path, but taking the probability into account to make this probability choice. But as you can imagine, when you are developing a system, you can choose the strategy, and there are different parameters that offer these models to make you the decision. And you can, for example, make the decision to always take the most probable path. And as a result, you will always receive the same answer when the question is the same. So this is very important. I have been talking that these models always predict the next word. But what we are used to are to the chatbots. The chatbots are the ones that you give a question, you ask a question, and then they answer you the result of your question. This is very different from predicting the next word. So the idea that we have here is that these LLMs that predict the next word are used to train new models. In this case, it's called fine-tuning. It's retraining these base models that predict the next word to be specialized on answering questions. So they are training with a lot, thousands, millions of questions and answers, and these models learn that they have to behave like answering questions. But they are based on these base models. Training a base model costs a lot, millions of dollars, a lot of millions of dollars. And retraining, fine-tuning models for making a chatbot is cheaper. So this is the strategy. And the idea is that if you have a base model, you can retrain, fine-tuning your model, not just for answering questions, for the thing that you want. So ChatGPT, the one that we know, or Gemini, or whatever, chatbot is based on a base model that just predict the next word, and then they are fine-tuned it, they are retrained it for behave like chatbots. Okay, some limitations that have these models is that they have a concept that is the context window. You can ask a model whatever, and they are able to answer you, and a lot of times they answer the right answer. The problem is that if you start talking with a model, for example, I start talking with ChatGPT or Gemini, and I say to ChatGPT, I'm Javier. I start talking with ChatGPT for hours. In one moment, I will ask the model to remember my name, and this model is not able to remember that my name is Javier. The reason is this context window. These models can process in real time a limit number of tokens. So inside a conversation, they have a very bad memory. They have a very good long memory because they have been trained to answer things, and they can remember the king of Spain, for example, in the last century. But they cannot remember my name because this short memory only they only have it for my conversation, and they are only, and this context memory, this size memory, is a limit memory, and it's not very huge. However, this memory has increased, and now in some models we can process 1 hour of video, and these models can remember all the things that happens in 1 hour of video that they have not seen before, or 700,000 words. That's a lot of books. So they can remember a lot of things, but their memory is limited. If they have been trained with this data, they are not going to know this data because they have been trained with this data. But the new data that we are adding to the model, they are not able to acquire to their knowledge. Just they can acquire them for the context window for a limit time. Okay, so this is very important. Another limitation of the LLMs are the hallucinations. They always are going to answer the question, but the answers are not always right. The problem is that they are very convincing and they look that they are right, but sometimes they are not right. And the hallucinations that are the most dangerous are the ones that you believe. The ones that are very clear that they are hallucination, they are not dangerous. But if you believe in an answer that it's wrong, but you don't know it, then there is a problem. So this hallucination is a problem. In this example, I asked the model, the ChatGPT in this case, how many gold medals did Spain win in Paris 24? And in the first try, it answered me that Spain won 6 gold medals. I don't know how many gold medals Spain won. So I can believe that this is right. But if I check it on the internet, I will see that this is not right. So it's an hallucination. And this is an hallucination caused because the model has not been trained with new data, with this newest data. So they are not going to being able to know this answer because this answer is not in their training data. That's why they cannot answer questions in real time. They cannot know your name if you write in the model your name and then you start to ask a lot of things and then you ask the model to remember your name. They forget your name because the limit size of the window, the thing that I have showed you before. And in this case, it's the same. I have not provided the model the information that Spain has won 5 gold medals. I don't remember the exact number right now. So it cannot answer you the right question, the right answer, but they answer something. So this is an hallucination, and this is a very big problem that this kind of models have, because we can believe things that they don't know. In a second chance, I asked again the same question, and here it tells me the truth that as of his last update, the Paris Olympics hadn't occurred yet. So it does not have the information to answer you. So these are the same conversation 2 times, and in one it was an hallucination, and in the second one we can see the information obsolescence. That in the first case it was always the same. It was information obsolescence. But here, due to this diversity that the model has to answer, here it makes an hallucination, and here tells you the truth. Another problem is the lack of expertise in some areas. This model has been trained with all the internet, almost all the internet, so they are experts in a lot of areas, but maybe they are not experts in a specific area that they don't have a lot of information about during the training phase. So how can we solve these problems of obsolescence? The problems of hallucination is always there. You have to take care of it. But the problem of obsolescence has different solutions. One is make a fine-tuning, like the one that I presented for creating the chatbot. So you can make a fine-tuning to increase the knowledge of the model. So you can retrain your model with new data, with the Olympics data. And now the model is going to change a bit the parameters of the model, and it's going to be able to answer questions about the Olympics because it has been retrained, including this data. This is not valid for real-time data because fine-tuning, retraining a model, it takes your time. So for real-time data, you have to retrain every second, and that's not possible. Another possibility that it's really interesting is Retrieval Augmented Generation architectures, in which the model receives the information that has the answers previously in the conversation, and the model, with its capabilities to understand questions, can answer questions with that information. I will give you some examples and explain the architecture in the next section. But this idea is very powerful, and it's very used today to increase the knowledge of these models and to adapt models for specific solutions that companies have. So what's retrieval augmented generation? I think that with this slide you can understand it a bit. I'm an user of an LLM, but inside I will have a software piece, that's a retrieval augmented generation, that will make an additional thing. The thing is that I make the question, then I will ask that question to the LLM, but before that, I will search in my database or any source of information which information is related with my question. Imagine that I have a database about the Olympics of Paris, and I'm asking a question about Spain. So in the RAG, I will search in my database about information. I will search on information about Spain, and this database will give me the relevant items related with Spain and the Olympics to my system. And what I would ask the LLM is my question with these relevant items. These relevant items are raw items, raw information. I suppose that they have the answer. I don't know that if they have the answer, but I think that they have the answer, and in raw information. So in raw data, with not a structure. So the model, the LLM, will receive my question and all the relevant items related with Spain. So it's probable that they will receive the information about how gold medals Spain won in the Olympics. And the LLM now will use its capabilities of understand text, of understand questions, and will answer me that question with the information that I have provided the LLM. So here, maybe I have information about the gold medals, the silver medals, the people that won the football championship of the team, a lot of information. And the LLM will, with this information, will answer my specific question. And now it's able to answer a right question, a right answer, sorry, because they know now the information. Here is an example of this concept. I made it manually with ChatGPT, and this is the idea. How many gold medals did Spain win in Paris 24? And I included this information in a real RAG. What you are doing is asking a database, having the relevant items, and giving the relevant items to the LLM. But here, what I'm making is just to provide the information, the raw information to the model. So how many gold medals did Spain win in Paris? And I provide information. So United States, Spain, and now the model is able to answer me the right answer. Spain won 5 gold medals in the Paris 2024 Olympics. So this is the idea of RAG. This is the most simple RAG. You can build very complex RAGs, and this makes the models able to answer you real-time information or information that they don't know by default. Typically, this process is stored in a vector database. If you read about RAGs, you are going to see that they always talk about vector databases. Vector databases are databases that information is divided in small chunks. One paragraph, for example, is a chunk, and then this chunks is computed into vectors. Why they are computed into vectors? Because you can make operations, calculations with vectors. You can calculate distances between vectors. And when you are asking a question, you transform this question into a chunk, and you calculate the vector of this question, and then you make the distance of your vector and your database, and you get the chunks that are more similar to your question. This is the strategy to obtain information in vector database. And if you read about RAGs, you are going to find these kind of RAGs, that the ones that are made with a vector database. But this is not the only option. The idea of a RAG is that you can obtain the information from any external source. Yeah, so this is the idea of this webinar, but that why the context broker cannot be this external source. The context broker has a lot of advantages. The information is modeled in NGSI. So most LLMs, as they have been trained with all the information of internet, they have been trained with a lot of information in NGSI format. So they understand the NGSI format. So for them, it's going to be easy to process information that they are in the NGSI format. Another advantage of the context broker is that they provide you up-to-date information, so real-time information. And this information can be used with the notification system of the context broker to give to your system, to give to your RAG the information in real time. The context broker provides you more facilities like geolocation, time, information. You can filter by properties, entity type. So you can make this process of, from your question, getting answers from your context broker with all these filter capabilities. Or even you can have the context broker to provide you information, but its notification system. And what we will do is to use these answers, these entities in NGSI format to make the question to the LLM with the entities that are related with your question, and then the LLM is going to be able to answer you with that entities and your question. Another possibility that we have not explored yet, but it's also possible, is to build the NGSI queries using the LLM. So as the LLM has been trained with NGSI entities, and also he has been trained with the NGSI standard, it's able to build NGSI queries. So you can ask the LLM to build an NGSI query that is related to your question. But this is something that we have not explored yet, but it's something that we have in our mind. So this is going to be the idea that we are going to have here. We're going to have the same architecture of a RAG, but in this case with a spatial database that it's going to be our context broker. And the process is the same that I have explained before. But instead of a vector database, that is the most typical one, with the context broker. And now I'm going to give the floor to David, because David is going to explain you the specific implementation of FIWARE, of this RAG architecture with FIWARE, and also is going to show you a demo about Naples in a tourism use case in which we have applied this architecture. So David, the floor is yours.
Thank you, Javier. So, well, I'm going to explain, as Javier said, the implementation of these things into a FIWARE solution. So, next, the idea is to have an architecture. In this slide, I am showing how a FIWARE-based system can be designed to serve as a tourism application, combining real-time spatial data with large language models in order to enhance the user experience. So what we have here is, well, I'll explain the key components. Obviously, first is the context broker, is the heart of the architecture, and is responsible for managing and storing contextual data in real time, such as point of interest, weather updates, or another contextual information about the environment, for instance. Then we have here, as you notice, the shaded components. They are there like the weather registrations, third-party systems, IoT agents. So they are, in our case, in our implementation, they are left out, but they will typically provide additional contextual data. We left them out because we wanted to have a simple solution, a simple proof of concept. We work, instead of ingesting data throughout IoT agent or third-party system, we just feed the system with point of interest in NGSI through a script. So so as I said, this point of interest hold the core contextual information in our solution. So once we feed this point of interest to the context broker, it will store this information about different landmarks in a city, which obviously are essential for a tourism-related query, let's say. So we have here also an application. Is something that the user interact with. It visualizes data through a zoomable map. In this application, the user can ask questions like, for instance, recommendations on things to do or places to visit. The app ideally will, once it receives the question from the user, it will ask to the context broker for some contextual information. It will retrieve in real time geospatial data about the city, and it formulates the query inputs to be passed to the large language model. So in this case, once the model receives the query from the user and the contextual information from the point of interest, it will process this information with the whole machinery that Javier just explained, and it will return back an answer to be shown in the application. So in this setup is the minimal, let's say, architecture to have one context broker interacting with a language model. In here, in this slide, I'm presenting an overview of how entities are represented in this system using an NGSI format, which is the standard that allows the description of different objects of real-world objects as entities with attributes. So let's break down this entity. It's called point of interest. Is the type is a data model. It has obviously a unique ID. This follows an unstructured URN format, which is commonly used in the NGSI to define unique entities in the system. It has a type. It has some attributes like the title, which in this case is the name. Is the name of the place, the landmark we just modeled here, which is the Pompeii archaeological site. It has this entity of relevance is in this case is set to 0, which is used to rank or prioritize the entity among other points of interest based on some importance or significance, and it will help to perform and filter information in a query. Well, we have an image. Not all the point of interest have images, but this one, it has one, and it will be shown in the map. It has a price. I mean, is the price that the property or the landmark asks to visit this place. In this case, is 16 euros. It has geospatial data, like the location of in GPS coordinates of this point. Obviously, we have a description here, which provide truly contextual information, explaining that, well, in this case, this Pompeii's archaeological site was buried under ashes after the catastrophic eruption of the Vesuvius in the year 79. And we have obviously the information about the capacity and the occupancy of this place, which are, well, self-explanatory. So you are not, I mean, it's not mandatory to model a point of interest like this, but we choose to do it like this. Obviously, you can have more information like, I don't know, contact or main contact or telephone or, I don't know, opening hours and so on. Okay, here we have the interactions. I mean, it's a sequence diagram of how this application interact with internally with all the components. We have a flow between FIWARE system and other components. In the background, I mean, as I mentioned before, we didn't put in place IoT agent or third-party systems, but here is to show that, or to highlight that other system might be present and they could be part of a continuous parallel data flow. So for instance, the IoT agent could provide live environmental data like air quality or noise levels, or third-party systems might run in background, such as loading, removing, or editing point of interest while the system is working. As I said, these components in background are working in parallel with other part of the system and are continuously feeding the context broker with information. So the main flow starts when the user asks or interacts with the application. Either it could be zooming or moving throughout the map and asking a question. One thing to note is when the user zooms or moves the maps, the application send the coordinates to the FIWARE context broker in order to retrieve a point of interest in that specific area. The context broker obviously will return the information that it found in this geospatial area at this particular moment. This answer will be in NGSI format, and they are the entities that I previously described with the location, description, and the other attributes. So once the user asks the question, the application sends these questions to along with the point of interest to the LLM. So the LLM processes the question in conjunction with the point of interest and formulate an answer, which is after a while is sent back to the application, which will be displayed to the user. So this is the basic dynamic or message flow in this small application. So now I will try to show a live demo using the city of Naples, because we will hosting the FIWARE Global Summit in a few days there. So in this demo, I'll start by asking some question about the city, so basic information about the current place, how to get a general overview. Then I'll refine this query by reformulating the question to get more specific details. So as I drill down further, I ask to some follow-up question to explore more options and possibilities. Then I'll iterate over this option and refine the choices, showing how the system helps narrowing down decisions. And at some point, I will change the language to see how the system adapts to this. We will see that in a bit. Finally, I will ask I will create new entities in the system throughout a script, pushing the data to the context broker, hoping that the system could adapt and take them into account. So let's see, sorry, here. So I prepare some questions to be faster. So now we have the application. As I said, we have the map. We can zoom in it. We can have more. We can see more point of interest, or we can limit to a certain extent. Yeah, we can freely navigate the map, and the system will retry the point of interest and show them properly. So here will be the FIWARE Global Summit. Here, more in the near the port, the central area, we have the train station, Castelnuovo, the Royal Palace, and so on. So the first, and here obviously we have the right side, the place where we can ask questions about the city. So I will copy one question I have here. I will ask a general question about what can I do in Naples to the system. I am asking about recommendation or architectural landmarks, and the system receive the question with the point of interest, and it answer with some options. So now let's say that I want to dig deeper into the cost of these places, because I want to know how much they cost to visit them. So I ask this to the LLM. So this is perfect, because now we have not only the places but the prices, which it takes from the information stored in the point of interest that I previously shown in I shown in the entity. So now let's say that I want to drill down more a little bit and ask about free places, and I don't want to go to crowded places. So I will ask about just the free places with less people in there. So we have quite fast an answer. Is giving me some places. Well, we have here in Markdown. Sometimes it has it tries to format the output. It gives the places with the occupancy level, and they are sorted because they are increasingly in number of people. Well, in this case, we see that there is this one. It put it, although it's not the most crowded one, it put it at the end. But well, we know that the system sometimes has these kind of behaviors. So let's continue with more details. Let's say that I wanna ask about the top 3 places with lowest occupancy. I mean, this is regarding the information it gave me just now. Not all of the map, but the information in this answer. And it gives me the San Gregorio Church. It has a description and occupancy. Obviously, well, it gives me the coordinates. In this case, it took this information from the entity, even though I didn't ask it. Though, I mean, sometimes it retrieves extra information, but we have to take into account that this information at least is not hallucination, is information held in the attributes of the entities. Well, it respect the number of entities. I asked for 3, and it gave me 3 places. So I will continue digging deeper to get more information. Let's say that now I wanna the address, not the GPS, but the address. Let's say if it's possible to get this from the system. Let's say if we will see if it takes not only the GPS, but the name of the street. Yeah, in some cases, you see we have the address of the places. I mean, are the same places as before, but we have now the address. This is great. So we are getting more and more information. And with this RAG and this point of interest that we are sending to the system, we are avoiding hallucinations because this is real information taken from here. So let's say that I don't wanna see this markdown. Let's get rid of that. So I ask about this to the system and see if it can answer the same. Yes, that's it. So with a simple query, we can say get rid of the markdown and give me plain text. It will be easier to read. So this is the way to interact with the system. Let's say that now I changed languages. I will write a question in Spanish asking what can I do near the FIWARE Global Summit? Okay, take into account that now we are, for the system, we are observing only this part of the city. Let's see. And it answered in Spanish, obviously, because the question was in Spanish. But here, the system says it cannot find anything about this event. And this is consistent with the idea that for the knowledge of the system at this particular time is not there, the FIWARE Global Summit. So if I go a little bit more to the west, I'll find the summit here in this part of the city, and there are just 2 points of interest nearby. So I'll ask the same question, just removing the part where I say I'm changing languages, and see if now is able to get information of this event. And that's it. It found the point of interest. It found other 2 points of interest nearby, and it answered that we can visit these 2 one here, the Palazzo Donna Anna and the Posillipo Hill. The thing is here now, as you can see, it's come back to the markdown notation. Well, this is something sometimes it's difficult to avoid, but well, it happens sometimes. Just to finish the demonstration, let's say that I will switch back to English. I mean, it was just to show that the model can interact with in your local language. Let's say that I wanna grab something to eat nearby the Global Summit, and see how it reacts. It's still now talking in Spanish, and it say it cannot find anything. Let's say that I wanna the answer in English. But well, the bottom line is it cannot find any information near the event. That's because now we don't have any restaurant or local cuisine nearby here. So now I will execute a script in background just to simulate that the system is receiving more information dynamically. So there, and I update the map, just moving a little bit, and voila, we see here Asian food, sushi, trattoria di Vittorio, and local cuisine. So coming back to the last question, I will ask the same thing. What if I want to grab something to eat near the FIWARE Global Summit? And now with this information, it will hopefully answer that if we can visit one of these or all of these restaurants, like we see here. As you can see, it gave us the price range, the address, still in Markdown, but okay, this information is precise. And just to finish, I will drill down and say, okay, I just wanna, because we all know that Italian food, mostly in Napoli as well, is delicious food. So I wanna just local recommendation, local food, and hopefully it will answer something about this. I mean, rejecting the Asian or sushi food. And that's it. We have the Trattoria da Vittorio and the Pizzeria da Mario, which are those there, which are local, obviously. Okay, so this is just an overview, a small demo of the application. What we just created as a proof of concept. In summary, we can say that we have learned how to integrate large language models within a FIWARE solution. I mean, using a specific particular advanced model, which are LLMs, large language model. We use a technique to augment the information in the system using the contextual information of the context broker, using this RAG technique, this way enhancing responses. Obviously, the context broker is the part, it plays a central role managing this data, supporting this architecture. For this, in this case, apply to tourism, but obviously you can use in other domains as well. So finally, we have some resources. I mean, we published the code of all of this. You can find this the code and these slides in this repository. And if you want to see a video demo of the demo I shown, you can find it in this YouTube address. So thank you, everyone, and I hope that you enjoyed this webinar, and see you soon.